Great. Okay, so this is week 3, and I'll talk about something about canonical ensemble, basically the free energy. First, I will briefly summarize, I think, what you need to know about this free energy, and then give you 2 basic examples. Then give you 2 interesting examples, and share something I think is really interesting. Okay, as usual, feel free to stop me and ask questions. Just unmute yourself and speak out. Sure. Okay, right. So let's talk about canonical ensemble. So I think this is one of the most useful ensemble in practice. Basically, we attach our system to some, thermal reservoirs, which is kept at temperature T. Basically, it means our system has fixed temperature T. And usually in practice, this thermal reservoir is typically phononic thermal reservoir, meaning that, for example, imagine we have a system. The degrees of freedom we care about is the spin degrees of freedom. There are many spins. So spin is our system. Of course, definitely there's some underlying lattice, right? And at the final temperature, at some fixed temperature, this lattice will vibrate, and that's corresponding to the phonon, and that phonon kind of becomes a thermal bus for this spin system. It's very natural. Okay, so in the micro canonical ensemble, the quantity we look at is the entropy, which is maximized at equilibrium, right? So in the canonical ensemble, the quantity we care about is the free energy. The free energy is equal to E minus Ts. E is the energy, S is the entropy. Of course, you know dF equal to what? Minus S dt minus S dn, something like this, I think. Right. So how we calculate this free energy? We usually calculate the partition function, right? So partition function is the first quantity we need to calculate, which is nothing but the trace of this exponential minus beta h. Beta is the standard 1 over kBt. H is a Hamiltonian. Of course, this is equivalent to this some mu. Mu is the microstate. So I will show you 2 basic examples how to calculate this partition function. And once we have the partition function, we have everything. So for example, the free energy is given by the log of this partition function. There's some prefactors, kBt minus kBt. And also we have the free energy. Then we can calculate the entropy, which is the because entropy is thermally conjugated with this temperature. So we only need to take a derivative with respect to this temperature. This is the entropy. And once we have this entropy and the free energy, we can calculate the energy. Energy is given by from this expression, energy is F plus TS. Of course, this is equivalent to some more more straightforward expression of this. This one. So the energy can be calculated directly from this partition function V. That's all the formulas we usually use. Basically, the first quantity you can say is we need to calculate is a partition function. Once we have this partition function, we can calculate everything. That's the logic. So any question about this part? It's just a very brief summary of what you have learned. Okay, so let's look at two basic examples that you definitely need to know how to do it. The first one is our familiar system, basically two-level system, energy level system. I imagine we have n copy of this two-level system. The energy is 0 epsilon, 0 epsilon. And of course, we can write down the Hamiltonian. The energy is basically epsilon summing over Ni, I from 1 to n. So Ni can be 0 or 1. 0 means it's in the ground state, and 1 means in the excited state. By the way, this Hamiltonian is equivalent to the sigma z form Hamiltonian I wrote down before. Okay, so this one is more explicit, but the equivalent. So let's look at the partition function. Like what I said before, is nothing but the trace of this guy. Basically summing over all the possible microstates. The microstate here corresponding to n1 can be 0 or 1, n2 can be 0 or 1, and so on and so forth, right? This minus beta h is this guy, summing over I from 1 to n. So I'm pretty sure you know how to do this. It's very, by the way, this guy is nothing but expansion minus beta epsilon. This guy is n1 plus n2 plus dot plus n. It is expansion minus beta n1, expansion minus beta epsilon n2 minus beta epsilon nn. I just copy this expression. Right, so this guy is nothing but n expansion minus epsilon n power. So this n can be 0 or 1. When it's 0, it's 1. When it's 1, it's minus exponential to the minus beta epsilon. So this is our partition function for this system. Any question about this part? Okay, so
Oh, sorry, I'm a little bit confused. How did you, yeah, like how did you go from the sum of um, products to the sum to the power?
you mean from here to here?
Yeah.
Okay, so yeah, it looks quite non-trivial. You can check, for example, when capital N equal to 1, of course, is true. Capital N equal to 2, you can check it's also true. And you can convince yourself this is true. Yeah, once you see this kind of steps many times, you will kind of it's true. Yeah. Okay, good question. Yeah, yeah, yeah. You can check by yourself. Um, or equivalently, you can kind of physically it makes sense, right? Because this kind of n copy of the system is like independent of each other. So you basically take one system. This is a partition function of one system, and then take n to the nth power. There should be no kind of a cross term, whatever. Okay, so once we have this partition function, yeah, thanks for asking questions. Yeah, once we have this partition function, we can write down the free energy, which is kBt log v, which is kBt and log 1 plus this guy. So if we have the free energy, we can calculate what? Yeah, we can calculate the other stuff. Okay, another quantity we care about is the energy. Remember, we calculate the energy in our first discussion, also in the first homework, right? So the energy from the formula we know is given by this guy. Of course, you can calculate this free energy this energy from the F plus Ts. But I think this one is more straightforward because you don't need to calculate the entropy first. But from this guy is minus n partial and log 1 plus epsilon, right? And take a derivative of this guy is 1 plus epsilon and this minus epsilon exponential minus epsilon beta epsilon. So it's epsilon. So this at times this factor for both numerator and the denominator, we get 1, and on the denominator get 1 plus. So this is exactly what we have obtained in previous discussion. So any question about this system, this part? Yeah, whenever you have something, it's good to kind of work it out explicitly using some simple system. When this kind of two-level system is one of the simplest system we can have. Okay, so another basic example I want to work out for you guys is the ideal gas that we did it last time. So different from the perspective that we adopt last time, here I will use this canonical ensemble, basically calculate this partition function. From the definition is given by the trace of exponential h. It always looks like this, or for both classical and quantum statistical mechanics, right? So for classical system, for classical ideal gas, the state, the microstate is enabled by this Q and P. This trace meaning that we will integrate over this microstates. Basically, it's a Qi for this particle I, and Pi for this particle, also for this particle I. And this the particle is from 1 to n. There are n particles, we assume. And we also divide by this n factorial to count for this kind of a indistinguishable property of the particles. Right? We mentioned last time, and this guy is minus beta summing over I from 1 to n to m pi squared. Right? I believe this. Any question about this step? Okay, so just let me know if you have questions. Great. Right. So for this volume integral, for this Q integral, is trivial, right? Because there's no integrand, like the integrand only depends on this P. So for this part, we would get V to the nth power. Right. For each particle, we get a factor of V. And for n particle, we get n to the nth power. And of course, it's this factor here. I just write it down here. And another integral we need to do is this momentum integral. By the way, this is equivalent to this, right? The same trick. I just factor this, use x plus y equal to x, e exponential x times exponential y. So of course, all the particles are the same. So it's just 2 nth power. It's also similar to the this system. It's like you work out the partition function like for one particle, then take the nth power. So here is also similar. So for one particle, you have for the position part, you have one way, then take the nth power. For this momentum part, you do this integral and take the nth power. And, oh, by the way, here is 3. Right. I mean, I'm pretty sure you can do this integral by yourself because it's just a Gaussian integral, right? Yeah, you know how to do it. Okay, so I just write down the direct the answer for you guys. 2 pi m kbt. Right. So it was useful to write, remember this partition function is dimensionless quantity, right? Because it's kind of summing over exponential is dimensionless. So it's always good to write this guy in this form. N is a number, it's also dimensionless. And V has the dimension of the length cube. And lambda cube. So lambda is a has dimension of length. Lambda is given by h divided by 2 pi m kbt. Right. Of course, once we have this partition function, we can write down the free energy not free, right? And we can calculate the pressure, which is given by minus partial F partial V, because P and V are thermally conjugate to each other. And from this expression, you would get the standard PV equal to N kBT. And similarly, you can calculate the energy, which is minus naught Z partial beta, which will give us E equal to the standard one, kBT. Basically, we reproduce all the results we obtained in previous discussions using other methods. Okay, so any question about what I'm seeing here? Okay, I guess it's quite straightforward, right? Here, the purpose of this doing those two examples is to show you how to do this kind of a partition function, calculate the partition function from the Hamiltonian.
So, but I mean, you know, this is a simple Hamiltonian, right?
Right.
I'm assuming in general, in real research, you wouldn't be able to calculate it.
Definitely, yes.
So would you try to calculate it approximately, or would you just use something completely different?
Okay, so one thing that we generally use is the so-called Landau-Ginzburg theory. It's kind of a phenomenological theory. We write down some effective theory for the order parameter. For example, for the spin system, is the mechanization. You write down the energy according to the symmetry of the systems, right? Basically, as long as the system, as long as the term is annulled by the symmetry, then you can always write it down and kind of calculate from there. I will show you two examples. The two interesting examples is basically the Landau-Ginzburg theory. Yeah, you're right. In principle, those two. Okay, so those two examples are very, very kind of okay. I will say it's trivial, but you know, very basic examples. And in principle, if you can calculate this, what's the name? Partition function like this exactly, then okay, that means the system is exactly solvable. In practice, that's kind of a very rare. And so there are two examples I think is exactly solvable in this way, like a many-body system. Like one is the isomodel in 1D, and another one is isomodel in 2D. I think I mentioned it before. Basically, write down the Hamiltonian. Write down the Hamiltonian. Starting from the Hamiltonian, calculate this partition function directly. That is durable for those two examples. For other like many-body systems, I don't think there are any. Yeah. Whenever you find a exactly solvable model, is amazing. It's like it's quite very non-trivial. Of course, it's not like here are two examples are basically non-interacting system. If essentially it's a one-body system, right? That's why we can do it. Okay, very good question. Okay, so there one remark I want to mention is about this dissonance. Dissonance has a physical meaning. Of course, okay, so this is what we call thermal, the brush, how to spell? I think it's something like this. Wavelengths. Meaning this tells us the wavelengths for the particle associated with the particle in this ideal gas. So then we have two length scale in this problem. One is this lambda t. Another one is the average distance between two particles. I denote as L. L equal to the total volume divided by the number of particles and 1/3, right? Yeah. This is yeah. So if lambda t is much smaller compared with L, meaning that basically particles behave like a particle. The wave the feature of the wave feature is not prominent. Then this is a classical gas, right? And it satisfies the Boltzmann distribution. And you can say when we increase the temperature or increase the mass of the particle, and this thermal wavelength gets smaller, meaning that the system becomes more classical. That makes sense, right? As you crank up the temperature or increase the mass of the particle, it becomes more classical. And in the opposite limits, when your T is, when your lambda is larger than L, meaning that there's a wave overlap between two particles, then it tells us the quantum effect will dominate. And we cannot treat this gas as a classical gas. It's a quantum gas. Basically, it's a Fermi gas or boson gas. Depends on it's a boson or Fermi. So for the boson gas, there's a boson-Einstein condensation which can happen in this system, and there's some interesting stories you can study. I think you will learn this later on in this class when it's become a quantum gas. It's in this regime. So there's some, you can imagine there's some critical temperature and control this transition. It's a very simple, comments you can make by yourself. Okay, by the way, in this regime, of course, above calculations breaks down because we assume it's a classical gas and it's kind of a classical treatment. Okay, so now let me tell you two interesting examples. I think it's good to share with you guys. Basically, we can obtain some profound conclusion by make some simple argument about the free energy of the system. Basically, the quantity, the argument will based on this expression, F equal to energy minus Ts. So you can say when temperature is small, this guy, energy will dominate, meaning that the energy will control the state of your system. When temperature is large, your entropy will dominate, meaning that the entropy will control your system. You can imagine there will somehow some transition, phase transition from one state to another. But okay, let's look at the first example. Okay, this example is worth a one-dimensional system, and it's a spin system. And imagine the variable is the magnetization. And let's denote as M. Of course, this M is a function of X. X is this one dimension, the variable, right? And let's consider a Hamiltonian. It's one dimension, right? This is the standard non-Ginsburg Hamiltonian one can write down according to symmetry. But just let me write down first, and then I explain to you what's the physical meaning of each term. It's It's also very reasonable. Like this. So alpha 2, alpha 4, and gamma are just positive constants. We don't care. It depends on the details of the system. We really don't know. Okay, so the first two terms, if you draw the potential, it looks like this. And I denote this guy as a potential. Looks like this. Because we always want to minimize our energy, right? Meaning that there are two special m. Let's denote as m naught and minus m naught. It corresponding to all spin up m naught. The length of the magnitude is m naught, or all spin down minus m naught. They are both ground state of this system because corresponding to minima of this potential. And the last term tells us if we want to change the magnitude of this mechanization along the x direction, you need to pay some energy, right? That's basically what this Hamiltonian tells us. Okay, so let us look at t equal to 0. Basically, we only care about the energy. Let's forget about the entropy. So t equal to 0, the free energy reduced to this energy. At t equal to 0, what is the ground state? Okay, according to what I said here, we know it can be all spin up, all spin down. Oops. Right? That's the ground state. This will minimize this Hamiltonian. This is the energy, right? Okay. By the way, if you choose this one or this one, it will always break the symmetry of your original Hamiltonian. Originally, the Hamiltonian is invariant under m going to minus m, meaning that there is a Z2 symmetry in the Hamiltonian. This ground state will break this symmetry, right? Okay, so now the question we want to ask is this ground state stable at finite t? Let me tell you the conclusion first. The conclusion is this ground state, those two ground states are always unstable at finite t. It actually tells us there's always no phase transition in one dimension, in spatial one dimension. Okay, so let's say, okay, let us derive this conclusion by invoking this simple argument based on this free energy equal to E minus Ts, as you will. Okay, so to understand, okay, so the another thing you need to know is there's another possible solution configuration at final temperature is the so-called the soliton solution or domain O. So basically, you would imagine you can have this kind of configuration, right? All spin down up to some point, and then all spin, all spin up to some point, and all spin down after that point. This will also minimize your potential, right? Because minus m naught and m naught both will minimize our potential. So it can be part of the system is spin up and part of it is spin down. However, this configuration would give us infinite energy because of the last term. This del m. This term tells us we cannot change the configuration discontinuously. So the compromise between this potential and this last term will give us a configuration like this. This up gradually, sorry, this magnitude will gradually decrease, and looks like this. There will be a width, and this configuration, of course, corresponding to a solution, is called a soliton solution, and or you can call it a domain law.
So similarly, you wouldn't have this sort of state where they are just, you know, kind of like when we're talking about two-spin system are kind of randomly aligned, because then it's also punished by this gradient even more, right?
Right. The thing is, this guy, this domain all, okay, if we start with at final temperature, if we start our system in this ground state, in this up state, the domain all configuration will proliferate and totally destroy this ground state. The reason why it will proliferate is because the appearance, sorry. Okay, so if we put one domain all in the system, this will increase the entropy. Sorry, this will decrease your free energy, meaning that this process is favored by the system. So say the change in free energy by putting one domain all into the system. Let's look at the change in energy and change in the entropy. So of course, we know putting one domain all in our system is not an energy favorable, because you need to call some energy corresponding to this part, which is a constant. Let me write down the okay, I can write down the number for you, but I don't think it really matters for the argument. Okay, let's assume it's some energy epsilon naught. If, of course, at zero temperature without the last term, the free energy will increase, meaning that this process is not favored by the system. So there's no domain all at zero temperature. The original ground state is stable. At final temperature, we have this entropy. So by putting one domain all into the system, so what's the entropy gain we have? So the entropy we have is KB, not the number of ways we can do it, right? So how many ways we can put the domain all into the system? Assuming the width of the domain all is W, then the possible location for the domain all is the total L, is the length of the system divided by this width. This is the entropy gain associated with one domain all in the system. Is it clear?
One thing, so we're drawing like arrows that are aligned, but these aren't actual spins. These are like macroscopic averages over spins. That's why we can have like a smaller up arrow, because that's just an area with more disorder.
Yeah, every spin is actually some average of many spins. It's a kind of a coarse-grained field.
Okay.
Yeah.
Okay, cool.
Yeah. Of course, microscopically speaking, the length of the spin is fixed. So, yeah. As you will see, as you will see, this one-dimensional statistical field is equivalent to a quantum mechanical double well problem. I will do the map explicitly for you guys. That's very neat. Okay, so if you agree, you can say at thermodynamic limit, meaning that the system is infinite large. So this process will always decrease your free energy. That's what is favored, right? Meaning that the domain of the system will proliferate and it will totally destroy your original ground state. It's unstable. Meaning that there's no, so let's draw kind of a phase diagram. Temperature 0 to infinite large. Of course, at t equals 0, the ground state is always stable. However, as long as you have some small finite temperature, the domain law will always destroy your ground state. So within the finite temperature regime, you always get a paramagnet system. And this, of course, is also called disordered, meaning that the Z2 symmetry is restored. Even though we make this argument for this very simple system, the conclusion is true in general. There is no phase transition in 1D. Just based on this simple argument. Is it clear what I'm saying here? Okay, let me map this problem to a quantum problem. That problem, like the double well quantum problem, is more familiar for you guys, I think. So it's good to do it. Okay. By the way, the partition function for this problem is, the possible configuration is M, which you can think of as a micro state, right? And the free energy, sorry, the Hamiltonian, I just write it down, is okay. How to map to a double well problem in quantum? Okay, let's change our variable x. Basically, we map the one dimension, the spatial dimension, to a time, imaginary time. And we map this temperature 1 over kBT to h bar. And also we map this variable m to our position. So let's say what we will get. This m becomes q. This minus beta, sorry, it's 1 over h bar, becomes 1 over h bar. And this dx becomes I dt minus alpha 2, and m becomes q squared. This becomes q to the 4th. This becomes alpha I q dot square. So I square is minus alpha q dot square. So what's this guy? You recognize that this guy is, I factor out this minus sign and cancel with a minus sign in front of this I. So it becomes I h bar dt. So this becomes alpha q dot square minus. Let's denote this guy as the V, which is a potential. This is nothing but the kinetic term. So this is nothing but the action. So this is nothing but this propagator for particle in a double wheel potential. This is a double wheel. Right? Is it clear? What I'm doing here? It's a very simple map. Meaning that the mathematical structure are exactly the same. So the amount of work we need to do to solve these two problems are the same. And this is quite general. This map is very general. The general conclusion is a classical statistical mechanics in D spatial dimension is what was equivalent to a quantum field theory in D-1 spatial dimension plus a one-dimensional time. In this case, it's a 1D equal to 1 spatial dimension. Right? Remember, there's this 1D problem. And map to a 0 spatial dimension and 1 time. 0-dimensional QFT is nothing but quantum mechanics, right? This is just a comment. Okay, so now let's look at what the original problem looks like in this double wheel problem.
So I remember Yaroslav was talking about, what was it, whales, some rotation or something like that. Is that related to this?
Wake rotation.
A wake, yeah, wake.
Yeah, wake rotation, yeah. That's kind of a related, yeah. And if this stemma is a quantum stemma, the conclusion is different, and yeah, there are some interesting relations. Basically, the stemma theory is what was related to the quantum field theory. It's kind of a one-to-one correspondence. So you don't need to solve them separately. There was a very simple mathematical relation you can do. You can obtain by some kind of a simple tricks like what we did here. Okay, so let's look at by the way, I think the time is up, but I will continue anyway. So if you have other stuff to do, feel free to leave. Anyway, I will finish the discussion here. I think it's useful to do it. Yeah. Okay, so what I want to see here is, okay, let's look at this kind of a domain or proliferation problem, kind of a phenomenon in this double wheel problem. So basically, there are also two ground states. But we know from the basic quantum mechanics, the ground state is not cat L or cat right. It's the superposition of cat L plus cat right, right? How we think about it? Let's say we start. Let us initialize our state in cat L here. Then as time goes, it will tunneling to the right. If you draw the picture, time, the x-axis is the time, the right, the y-axis is the, is the position. Where is the cat? This can be L, this can be R. So at the initial time, it stayed at L, and at some point it will tunnel in to the right. And then it will stay at the right for some time, then tunneling to the left. It will keep going, keep doing like this. By the way, this is also a Thornton solution. and the people call it instanton. The reason is because it's like a solution localized in the time domain, so it's called instanton. So this particle will tunneling back and forth. After some time, you can imagine it will form a state like cat L plus cat R, right? It also tells us that Z2 symmetry cannot be spontaneously breaking in the quantum mechanics. So basically here you would imagine the Z2 symmetry will break in because it's a cat L and a cat R, but because of this tunneling effect, the ground state is L plus R instead of L and R. So this Z2 symmetry is restored, just like in this domain all case. The Z2 symmetry is restored by this proliferation of domain all. So here the Z2 symmetry is restored by the tunneling of these particles between two ground states. They're the same. And this tunneling effect people also call it a soliton, which is call it instanton. It's a kind of soliton. Is it clear what I'm saying here? Okay, great. Actually, there's a I think it's spend more time than I thought. There's a two-dimensional similar situation. It's I will very briefly mention it. It's like in 2 dimension, you have also it's kind of a spin system, and in this situation, there are some soliton configuration is called a vortex. This vortex proliferation will drive a phase transition. This is a very famous phase transition. It's called posthumous Solness transition. And those two guys won the Nobel Prize like 5 years ago because of this work. Yeah, theoretical work. And the argument, you can obtain this phase transition by looking at the free energy. Similarly, E minus TS. So you just look at what's the energy change if we put one vortex into the system. The energy associated with one vortex is scales with log L. L is the size of the system. There's some prefactors. And minus T, the entropy is also log L. So you can see now there's some critical temperature. And when T is smaller than A, meaning that the energy will dominate, tells us the vortex is not favorable in the system. So there will be no vortex. However, when T is larger than A, this guy is negative, meaning that the entropy dominates, tells us the vortex are favorable in the system, and there will be a vortex anti-vortex proliferation. It will destroy the original phase, and we get a new phase. That's a phase transition, and basically that's it. Yeah, it's called or KT phase transition. It's also called topological phase transition because this phase transition is very special. It's the phase is from coarse long range order to the short range order. It's not from long range order to short range order. Yeah, that's all I want to say. Okay, so any questions?
Yaroslav just talked about it yesterday in 241C.
Okay, I see. About this KT transition.
Yeah.
That's nice. So he also make this kind of a entropy argument or like a rigorous.
He did exactly the same. I mean, he actually calculated things.
Okay. That's did he talk about this kind of domain law stuff?
We talked about the XY model. We didn't talk about one-dimensional.
I see. But kind of in the same spirit, I guess.
Yeah.
Yeah, it's that's good. Yeah, great.
All right. Thank you.
Sure.
See you.